Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Hi everyone. So today Madam going to give lecture on chapter 7, topic of magnetism, where Madam divided it into 3 parts. Okay, part 1 up to part 3. So today inshallah I'm going to give you lecture on part 1, where subtopic involved is 19.1, 19.2 and 19.3 on 19.1, 19.3 and 19.4. Right, so let's begin. So magnets, before we begin every topic, of course we need to know the basic criteria or properties of the magnets. So for magnets, you have poles, 2 poles of magnet at the end of it, the magnetic bar for example, okay, where objects, ferromagnetic object are most strongly attracted to it. Okay, the pole named as North Pole and South Pole. Right. Another character of the magnet, like poles going to attract each other, like poles going to repel each other. Okay, and then unlike poles, okay, attract each other. For example, north and south going to attract each other. But if north meet north, then it's going to repel each other. This is similar to electric charge. Okay, if you have a positive meet positive, then they are going to be repelled away. If you have a north pole, okay, of one magnet, another north pole from another magnet, the pole going to be repel each other. It's going to experience, okay, opposite force. Right. But then if you have positive charge meet negative charge, or you have north pole meet south pole, okay, then they are going to attract each other, right? So they will be attracted to this, they will be attracted to this. Okay, this is the meaning of the characteristic. However, okay, for the next characteristic, magnetic poles cannot be isolated. Let's say you have originally this length of permanent magnetic bar. Okay, this is north, this is south. You cut into half. Okay, you cut into half. Still, you're going to have north and south, north and south. You cannot have one single pole. Okay, you cannot have north only or south only, which is opposite to the point charge in electric. We do have positive or proton alone or negative or electron alone. That is the difference, right? Unmagnetized material can be magnetized by stroking it with a magnet. This is similar approach to like we want to charge a metal, a conductor, by stroking it with the charge conductor, with already charged conductor. So this is similar approach. Okay, but then of course you need to have a lots of stroking process. Okay, it's not like stroke 2 times then you will get magnetized material. No, you have thousands of times. Okay, many times. All right, then for another method to have to have a magnetized material, by using induction process, where you can place the material near a strong permanent magnet. Okay, and you put it there for a very long time, 10 hours, 10 days, or like that. Okay, then the material going to be magnetized. Okay, by referring to the method of the magnetizing the material, we can conclude into 2 types of material. Okay, so how easy, how hard to magnetize a material, based on that facts, we're going to classify the material or put it as two types of material. We have a first one, soft magnetic material such as iron, easily magnetized, but then also tends to lose their magnetism easily. Okay, so pro and cons lah, right? So for hard magnetic materials such as cobalt and nickel are very difficult to magnetize, but they also tend to retain their magnetism for a longer period compared to iron. Okay, next one will be sources of magnetic field. Okay, the most common that you use to is permanent bar magnet, right? Permanent bar magnet is actually an alloy coming from the earth core, okay, due to very high temperature and pressure. Okay, the permanent bar magnet become magnetized. Okay, that is the most common that we use to. Okay, but actually we do have another source of magnetic field where the region, the field of magnetic field, okay, exists in the space, okay, or within the region of space surrounding a moving charge. The most important here is moving charge. Okay, includes a magnetic field. Not to forget, okay, if there is a charge surrounding it, also will be electric field. This is our previous lesson, yeah. But then the electric field exists. Doesn't matter whether the charge is in motion or static. Okay, but for magnetic field, it only exists whenever the charge is in motion. Okay. Magnetic field surround a properly magnetized magnetic material. This is the one that Madam said just now. For example, permanent magnet. Right. So magnetic field. Okay, magnetic field is imaginary field. We cannot see physically by our naked eyes. So what we should do in order to visualize the magnetic field is by using a needle compass, a very small needle compass placed all over or surrounding the permanent magnet here, for example. Okay, so the direction of the needle compass going to be traced out and representing the field lines. Okay, the green color here. So it seems like all the time that the field lines originate or coming from North Pole, entering or ending at South Pole. Okay, so permanent magnetic field is vector quantity. Okay, normally we use symbol capital B and arrow on top of it. Alright, okay, so this is the symbol of the magnetic field. So if I'm not mistaken, you already done this experiment in your primary school where you have iron filling, okay, distributed all over a permanent magnet. You will see the pattern, okay, the pattern that going to be produced by the iron filling representing the field, the magnetic field surrounding the permanent magnet material. So this is for a permanent bar magnet. Okay, this is for opposite pole. Okay, north, mid, south. So it's similar to dipole. If you still remember what is dipole, dipole where you have positive charge, mid, negative charge. So this is a similar pattern to this, right? And here you have a same pole, north, mid, north, so repelling each other, right? So magnetic field line, when a charged particle is moving through a magnetic field, a magnetic force acts on it. So this is also another way to detect whether there is a magnetic field or not within the area. We move a charged particle or we project a charged particle into the field, into the area. Okay, if the charge going to experience a force, mean that exactly surrounding or within that area there is B or magnetic field. So by this definition, magnetic field is actually a ratio between the force experienced, okay, by a charge, a moving charge, to its velocity. B is equivalent to F over Q V sin theta. Okay. Or if you rearrange this, okay, F equivalent to QVB sin theta. Okay. Why is this a sin theta there? Actually, F here is a cross product. F here is a product. F is actually a product where you have QV cross the B. If you still remember your math. Right? So the magnitude of the F is magnitude of QV B sin theta. Theta is the smallest angle between the velocity and the B. Okay, so theta is the angle between the V and the B. Okay, why not Q? Q is not a vector. It's similar analogy to mass. All right. Another unit for the unit for B is Tesla. In Tesla, it's quite big unit. Commonly used is Gauss, the CGS unit. 1 Tesla is equivalent to 10 to the power of 4 Gauss. Right? 10 to the power of 4 Gauss. So here, okay, 1 Tesla is equivalent to 10 to the power of 4 Gauss. Right. And then if you recall back the electric field lines, there is electric flux, right? Okay, so similar to magnetic field, there will be also magnetic flux. Okay, the unit of magnetic flux is Weber. So if we refer to the dimension analysis of B, okay, is equivalent to Tesla in SI unit, where it is actually a derived unit from Weber over meter squared. Okay, equivalent to Weber itself is Newton over Coulomb dot meter per second, which is equivalent to Newton ampere dot meter, because Coulomb per second is ampere. So this is the basic unit, the fundamental unit for B, magnetic field. Okay, this is the derived unit. Tesla is the derived unit. This one is derived unit for magnetic field. This one is the basic unit of the magnetic field. So, what we have to do before you substitute everything here, you must put everything in SI unit. Then you will have Tesla unit in this case for B, right? Okay, finding the direction. That is for magnitude just now. So now the direction. Okay, the direction, right? The direction. Right. The direction by using Fleming right hand rule number 1. Okay. The F is your thumb direction. Your index finger. This is your index finger. Is the velocity direction. Then the rest of your 4 fingers, okay, will be the direction of your B. Okay. Alright. So as we recall just now, okay, F is actually a cross product between QV and B, right? Okay, so represented by this diagram. Okay, by this diagram. V and B within the same plane, the yellow plane here, okay, or page, right? The F must be perpendicular to the velocity as well as to the magnetic field lines. Okay, so F always perpendicular to the velocity and the B, the magnetic field, right? The angle, the theta, is the smallest angle between velocity and magnetic field, right? So hopefully this is clear. Alright. Next one about the direction is about this one, symbol, denotification of symbol. Okay, for dot symbol like this, okay, representing direction of out of the page. Okay, for cross symbol like this, representing direction into the page. Okay, into the page. So it represent what? It could be direction of velocity, it could be direction of B, it could be direction of F, any of it. Okay, so it's not all the time about B only. It could be also the velocity, the force as well. Okay, dot representing out of the page, cross representing into the page. For the dot, this is analogy of an arrow actually. Okay, so if an arrow is moving out of a page, okay, so you will see firstly will be the tip of the arrow, right? So it represented by the dot, okay, symbol of dot. And if an arrow is penetrating a page, okay, what will happen? You will see the tail of the arrow, where it's represented by cross symbol. Okay, so let's try out this example. This example or exercise, madam, take out from your textbook. All right. This is question at the back of your textbook, chapter 19. This is question, if I'm not mistaken, question number 4. Question number 4. Right. Page 649. 649. Okay. So the law that just now, okay, this one, by default for positive charge. Positive charge. Okay. What will happen if you have a negative charge electron in the problem solving? So all the direction that you have finalized, okay, according to the rules, just reverse it. Okay, what do I mean? Let's take a look on this. Figure A. Alright, you have B into the page. Okay, B into the page. Your index finger is on the top of the screen or page. Okay, so your B 4 fingers, the rest of the 4 fingers entering the screen or page. So your thumb is pointing to the left. Right, so your thumb is pointing to the left. This will be the direction of your force, provided that positive charge is entering, okay, the field in this way. What will happen if you have a negative charge? If I have a negative charge, okay, so the direction of it just opposite. If you have positive charge, you just follow exactly as the rules, Fleming right hand rule number 1. But if you have a negative charge, okay, please, okay, reverse the direction that you get according to the rule. Okay, that is how to do. Right, for figure B, let's try everyone. Okay, your velocity, the index finger to the top of the screen, your B is to the right, so your thumb, okay, is pointing into the page. Your thumb is pointing into the page. Alright, your thumb is pointing into the page. So this will be positive charge, positive charge. Your thumb is pointing into the page. Okay, so that will be the direction of your F. Right. Okay, you will have for third one, C. Okay. Okay, B is downward. Index finger downward. Okay, velocity to the left. So your thumb will be out for positive charge, yeah. Will be out of the page. Right. You may try this one as well for positive charge. Okay. The force going to be in this direction. Right. Now, please try exercise. This is question number, if I'm not mistaken, number 5, yeah? This is question number 5 in your textbook. Alright, so you have force on the top of your screen. You have velocity to the right. So by right, your B is out. Sorry. Your B is into the page, isn't it? So your B everywhere here, like this. So B. Okay. For this case, okay, to have velocity out of the page, okay, velocity index finger, your thumb is your F, okay, so your B should be in this direction. Right, and then for C, okay, your index finger is into the page or screen, your thumb to the left, so your B will be somewhere like this. So this is your B. Right then. Okay, you can try out this one, okay? What will happen if the charge is negative? So, whatever the answer you have, just opposite of it. Okay, just reverse of it. Okay, next one, 19.4. Motion of a charged particle in a magnetic field. If let's say, alright, a charge is moving, okay, and enter an area with magnetic field, which is into the page. Okay. Okay, then like this one. Okay, let's say the charge is moving to the right, so the B is into. You will see that the force going to be experienced by the charge is to the top of the page. Okay, if you analyze another position, which is here, okay, again you will have the force in this direction. Any position, okay, you will have the direction of the force within this blue arrow. Why is this happen? So the moment the charge at this position initially, okay, the force is to the top of the top of the screen, okay, but then the charge cannot turn 90 degrees because it has to obey conservation of momentum, so it's going to be bent. All right, at this position again is not going to turn 90 degrees and follow this F, okay, directly. It's going to turn or bend again and again and again. Eventually the charge going to move in a circular path. Okay, so since this motion caused by the magnetic force on the moving charge, right, so the formula, the force experienced by the charge is Q VB sin theta. However, sin theta become 1 because it's sin 90 degree. The angle between the velocity and the B is perpendicular. Okay, it's 90 degrees. So sin 90 is equivalent to 1. The force here also, okay, a kind of circular motion because the path taken by the charge now is a circular. So this F is also FC. Okay, equivalent to F magnetic. What is FC? mv square over r. Equivalent to QVB. Okay, so from here, you're going to have the R is equivalent to MV over QB. This is also known as cyclotron equation. This is on how to get the radius of the circular path taken by the charge. Okay, whenever it moves in a circular path. Okay, in real life, if let's say the velocity and the B is not exactly perpendicular, the path taken by the charge going to be helix, okay, or spiral path, okay. But then for your syllabus, we're not going to discuss this one in details. Exercise. All right, for exercise here, okay, you may try on your as your homework, yeah. Okay, please try this one as your homework. Okay, additional of it, okay, as your task here, please solve question number 7. Okay, question number 7, page 649. All right, this is your homework. Okay, and another one additional of this is question number 7. Okay, page 649. Okay, so that's it for today. Thank you very much for your time. Do consult me if you don't understand anything. Okay, all the best. Assalamualaikum warahmatullahi taala wabarakatuh.